Hi everyone, I'm Leah. For my Lab 5 project, I'm investigating the physics of animation. We often see cartoon characters defy gravity for comedic timing. So my purpose is to use VPython to quantify the extra force required to make a character hover in midair compared to a realistic model governed by the momentum principle. The system involves two objects with identical properties, a mass of 110 kilograms and an initial upward velocity of 3.5 meters per second, which I estimated from observational data of cartoon jumps. I used two distinct models, a realistic model where the net force is solely gravity, and a cartoon model where a temporary upward force is applied at the peak to create equilibrium, meaning the net force becomes zero. Using the momentum principle, we can predict the behavior of both objects. For the realistic model, the constant gravitational force of 1078 newtons downward causes an immediate change in momentum back towards the ground. For the cartoon model to stay suspended, my prediction is that an exactly equal and opposite upward force of 1078 newtons must be applied, resulting in a zero net force and zero change in momentum. I translated these models into VPython. In the code, I used the Euler-Kromer method to update velocity and position. While both start with the same momentum, the orange sphere enters a conditional loop at its peak height that applies the upward force I calculated. As the simulation shows, the realistic model returns to the ground in under a second, whereas the cartoon model remains suspended, successfully modeling the hover effect seen in animation. What does this mean for our understanding of physics? It shows that comedy in animation is essentially a temporary override of the momentum principle. To answer a what-if question, if we increase the mass of the character, the required cartoon force would have to increase proportionately to maintain the hover. This highlights that even in a fictional system, the relationship between mass and force remains the essential governing factor. This project demonstrates that we can use computational modeling to bridge the gap between idealized physics and stylized reality.